In this video, we're going to continue our work in section 8.3. So we have a box here for theorem with p-series test. I'm going to go ahead and skip that over in this video. The workbook is a little bit out of order here. This should be below this example. So we're going to focus on example 6 in this video. All right, so example 6 says, so we're not going to use the whatever the p-series test is at this point, but example 6 says prove whether or not the series given by n equals 2 to infinity of 1 over n times ln of 2 converges. Okay, so we're not told what theorem or statement to use to show convergence here. So far, ignoring this theorem, so far what we do know what to work with is the integral test and the comparison test, or rather the divergence test. So we only have those two tests behind us. Okay, so I'm going to scroll down back to our example. So we need to use one of those tests to determine if the series converges. So what we're going to do is start with just playing around. So we're going to write out just some scratch work here. So I'm going to try to determine which theorem or test we can use. So kind of the easiest one is to consider that divergence test, div test. So what does that mean? That means we need to look at the limit as n goes to infinity of the terms in our series. So 1 over n ln of n. Okay, what happens there? Well, here, the denominator n and ln of n, that just goes to infinity. So then the fraction itself, 1 over infinity, goes to 0. So then if we look back at that divergence test, if those terms go to 0, then our series could converge or diverge. So we say that this result, the limit goes to 0, means we have it's inconclusive. So the divergence test doesn't give us any info. Doesn't give any conclusion. If these terms had not gone to 0, then we'd say for sure, yep, this series diverges. Unfortunately, these terms are equal to 0, so no conclusion. Okay, so that's okay. Let's see if the integral test will help us. So for that, we want to set up that improper integral. Here we're going to start from 2, because we want to look at if this 1 over n ln of n is equal to our f of n, that n is starting at 2. That's just so we can, in fact, plug in 2. If we plugged in 1 there, the denominator would be 0, which we can't do. So just a small point, we need to start at 2, go to infinity of the integral of 1 over x ln of x dx. Okay, so that means that will be the limit as b goes to infinity of 2 to infinity of 1 over x ln of x dx. Okay, so we need to compute this integral. So we need to dig deep back into our Math 152 or Calc 2 thoughts where we're computing these improper integrals or integrals in general. And we'll see here that a u sub is actually what we want to do. So if we let u equal ln of x, then du nicely works out to be 1 over x dx. So we can make that substitution. So then that means the limit as n goes, as b goes to infinity. I'm not going to change my bounds of integration here. I'm going to let this continue to be x equals to x equals infinity, just because I'm going to move everything back into x world anyway. I don't need to change the bounds when I'm using that u sub. And in fact, I probably don't even need to go into detail here, but I'm just doing this extra step for us. So when we do the u sub, we look like 1 over u du. So then we just need to compute the antiderivative there of 1 over u. So the antiderivative is ln of u. So that's going to look like, back in x world, ln of x, because recall u was equal to ln of x. Okay. And feel free to pause the video and work that out a little bit more on your end. So then we're evaluating at 2 and b. Okay, so let's continue here. So So when we evaluate there, we get the limit as b goes to infinity of ln of b minus the ln of 2. I need to determine what that value goes to. So here, ln of 2, that's just a finite number. So we can just write finite number. But the ln of b, well, as b goes to infinity, the ln also blows up. And as the input in ln blows up, goes to infinity. I encourage you to look at a graph of ln of x to convince yourself that that is true. So then this whole limit goes to infinity, which means that improper integral diverges. So what does that mean? Well, we know that that improper integral diverges. So that tells us that our series diverges. So now we're ready. And maybe before I do that, I'm just going to say, therefore, our series diverges. And that's just kind of like a note to self to know kind of where to go in the end for this proof. So that will be the result. Now we're ready to set up that formal proof. So let's get started. Proof. All right, so since the improper integral from 2 to infinity of 1 over x ln of x dx, since this diverges, this means the series from n equals 2, this time n is starting at 2, to infinity of 1 over n ln of n also diverges. And that is by the integral test. All right, so here is our formal proof. And we can just be sure that we've included everything important. So yes, indeed, we are using complete sentences. That's kind of number 1. Number 2, we're using our correct notation. So everything that I write down is not just true, but I'm using the proper notation to go along with it. I'm including my work clearly shown up here. And I'm stating the theorems and results that I use. Awesome. Great job going through this example.